Well, I think it's time to get going, so let's go for it. We were talking about hardware, really, what are the parts of a gas chromatograph, a little bit about how they work and so on. We've gone through the most common detectors, and so we've got a couple still to go. I think I mentioned the chemiluminescence as one of them. Sulfur compounds are really important to us in the flavor business. They're very, very potent compounds. And so very commonly, if there's some free sulfur, some volatile sulfur, it's a problem to you. So we are interested in, there are two detectors that do very nicely for that. They tend to have very high sensitivity and a lot of specificity. This is chemiluminescence. In this case, the reagent gas is fed into a flame, and your compound is burned in the presence of this reagent and gives off a certain wavelength of light that you monitor. So kind of what's given off as an indicator is enhanced or caused by the reagent gas. The other type of sulfur detector is a flame photometric detector. In that case, you simply have a typical flame ionization detector. You have your air in, hydrogen in, flame burn, and there's just a photomultiplier here. Not a photomultiplier, but probably just we call it photomultiplier. But it has a filter on here, so it only picks up wavelengths when you burn sulfur. So in one case, we kind of have a reagent gas that enhances the response. In the other case, we simply monitor that response by using this filter that does the job for us. We were to the point talking about mass spectrometry or mass spectrometric detection. And that's been an exceedingly useful tool to us as a detector. And if you go down in our lab, every mass spectrometer we have, or almost every GC we have, it's also connected with the mass spectrometer. That's just a marvelous detector, and I'll go through why that happens to be the case. It basically not only gives you a line on a piece of paper and say, guess what, something came out here. It has the ability to tell you what came out there. And so that's a big step forward. So it's a really desirable detector, exceedingly useful. I'll give some examples of that. So, like I say, the GC draws a line on some kind of a screen or whatever, but it tells you nothing more than that. The mass spectrometer gives us more information what that compound is. So identify compounds that come out. And also, you can selectively quantify a compound without separation, without absolute separation, which is absolutely fascinating to me. I hope you'll follow along with this. It's a little bit of lines and whatever that come up and maybe not overly clear. But this is the chromatogram that comes out of the gas chromatograph. So we're coming along, here's the compound, here's the compound. And we're interested, let's say, in just one portion of this, and it would just be a little portion right here. So this little portion right here is blown up there. And then, in fact, only one of these, this last one here, tends to be blown up here, but it didn't take the green one for discussion. It didn't take this one. It took just the two top lines for demonstration. So if we look at our gas chromatograph and watch our recorder on the screen, comes up like this and goes down. And if you would take a look at that, you'd say, oh, that's one compound. It's nice symmetry. You always look at the peaks nice and symmetrical, or are they kind of lopsided, like there might be something else with it? That can give you a really nice symmetrical peak. But guess what? If you look at it, this line is like they made up to them. And so it's absolutely misleading to think, that that's one compound. Maybe you got a good identification there someplace. Well, guess what? It may be. But the neat thing about mass spectrometry as it's evolved is that you can get spectra. You can take these molecules, blow them into pieces, look at the pieces. You can do that really quickly. And so basically that's what you're doing. You're taking the gas chromatographic effluent, hitting it with really high energy, explodes the molecules, and then the mass spectrometer puts the pieces together or you measures the pieces. And so by that, we can see, okay, there's a set of pieces that fit this particular compound. There's another set of pieces that fit this particular compound. And what the mass spectrometer does, it looks for things that are moving perfectly in symmetry. And so all of these ions, all of these fragments, bits and pieces that blew up, come out at exactly the same time. Poof, they're there. But there's another set that poof, and a little bit later they're there. And so this is only differs. The top of this peak to the top of this peak differs by 0.25 seconds. And the machine says, hey, the set of ions is moving differently than these. And so the machine looks at these ions separately, they're moving, and these ions. So there's no separation of that peak. We've never quantified that with the gas spectrograph. But all of a sudden, the mass spectrometry tuned to look at just that. You just look at that, and you can quantify a compound without two compounds there, without ever separating them. That's pretty darn neat when it comes right down to it. This is just a little more information on that one. But there's what we saw in the previous one. And if we look at the two sets of fragments that are coming together, traveling together, one set of fragments is here, and that happens to agree very nicely with a compound, the cyclohexane, 1-ethyl-2,4-dimethyl cyclohexane. So this set of ions are for this compound. The ions that occur up here that have 69 methyl and 111, therefore heptane 2,5-dimethyl. So you find out what compounds are. You don't necessarily have to separate everything. In the world we live in, there's an awful lot of compounds around the world. A lot of compounds that can be coming out. Because you get a nice peak on some instrument doesn't mean it's pure. It means you got one peak. That's all it means. It doesn't mean it's pure. So the mass spectrometer has just done tremendous at making things much easier, making things analysis much more accurate for us. And that's within maybe the last 15 years that we've had that ability. So it's not new, but believe me, it's not old either. So detectors, they're extremely important to us. And we got some nice tools. Our problem oftentimes, though, is the idea of how do we separate? How well do we separate? And we like to do that. And we like to do it by the column. Ideally, let's not make life difficult. Let's try to get one compound per peak, okay? And we can do that much of the time, but not always the time. And so over here is our resolving, our resolution. We do a mathematical equation on the sheet that is loose. And so we do a little bit of math on it. And so we start looking, these are the factors that determine our resolution. And that we want this high. We want a big number here. And so how do we get a big number? This is selectivity. That's determined by the column coding. How selective is that column coding for the particular analytes? And we always try to use a column. Say there's probably 4 columns that are used generally. One's very polar, so it interacts with polar compounds. The other interacts with non-polar, and then in between. So first of all, we work with selectivity. We work with a good column. We work with the right column to get our separation. And that gets into this term. This is one that's kind of trivial, I guess, in a sense. And that's how close to the solvent does it dilute? Is it coming out real quickly? There's very little interaction. Here comes your solvent. You get this big peak, and then there's maybe a peak of interest. But you don't have much time for interaction. You don't have much time for separation. It spends very little time in the column before it elutes. And so, again, we look at our stationary phase. We look at the compound itself. Because a compound is very volatile. It's going to come out very quickly. So, again, how soon, how close does it elute? This is the one we work most with. So we do work with the column phase, and we do look at the efficiency of that column. How good of a column do we have? If we've got a poor column and our peak comes out something like that, it's kind of hard to get separation of things. If it looks like that, okay, we can put 1, 2, 3, 4, 5, we put 50 more peaks in here and get resolved if we have a good, efficient column. So let's take a look at that. This idea of column performance is typically measured by 1 of 2, well, by 2. Oftentimes, people intermix these two, but they do the same thing, but do it a little differently. Efficiency, so column efficiency, is the number of theoretical separations you can get per meter of column. So you want that number to be big. We want a really high efficiency column, lots of units of separations that occur. And so we want this number big. This is a different term that may be used. It's height equivalent for theoretical plate. In that case, how much of our column does it take to get a unit separation? If it takes this much of our column to get a unit separation, that's not very good because the column isn't long enough. If it's that much, now we get lots of units of separation. So this one we want to minimize. This one we want to maximize. So the difference, and when we look at some figures that are coming up, high is good here, it's bad here. Oh, I'll point that out. So what influences our efficiency? How well that system runs. So let's say we've got one of the variables here, and this is the column size. We use capillary columns. So have you been in the, no, you haven't been in the GC lab yet, have you? I think that's coming up. Well, you're going to see these columns, and they are 0.25 millimeters. That's a small diameter column. And so why do we work with 0.25 millimeter? Well, if you think about it, if you got a very small hole, a small tube, the gas tends to be fairly uniform. If we got a big one, we can have some gas flow through the center, high, a little slower as we go up to the sides. And so the bigger the column, the more mixing, the more we get these peaks stretching out, our compounds stretching out during the run. And so we like to work with a small diameter column. That's more efficiency. 0.25 millimeters, our workhorse, it comes out here. That would be better, but there are reasons why we really don't want to do better than that here. It costs us in other ways. So 0.25 is our compromise. Bigger columns, less efficient, less efficient. So again, pick a small diameter column, don't make it so small where you have really problems with overloading it. The column phase doesn't work well for you. So just a rule, work with a fairly small column. Don't go to the big ones unless there's some reason you must. This is now just the opposite. Here's our HETP. So this one we want to minimize. The last one we wanted big. This measure we want small. And so this looks at our carrier gas. I think I mentioned probably last time we were here, Monday, that the different gases that are used, and I said different carrier gases, mobile phase gases that we use. Traditionally, we work with helium. Again, you can't get helium very easily. So what do people do? They use a different gas. So what do you want to use? What's a better choice than helium? Well, here's nitrogen. We want this to be minimum. The lower, the better. And then nitrogen looks really good. Look how low that is. That's lower than this or this. This is our best carrier gas to use, most efficient. But this says, how fast is that gas moving through the column? How much time is this going to take? If this is going at 10 centimeters per second, it's going to take me a long time to get this compound out. My separation is going to take me a long time. If I can boost it up here, well, let's get up to 60, 70, 80 centimeters per second. It takes 1/8 of the time to run it 80 centimeters per second versus 10. So, okay, I like the time. How much does it cost me between here and here, the separation? It costs me some. Yep. I get better resolution down here, but I don't get really bad up here. So let's go with helium. Well, long ago, we decided that wasn't a good deal either. What about hydrogen? Here's our hydrogen coming down here. It isn't quite as good as nitrogen. It isn't quite as good as helium at their best. But I don't want to hang around the GC all day and wait for heat to come out. So I push it, I get that gas mobile phase, truck it down that column. And look out here, we can be 80, 90 centimeters per second. We cut our time by a factor of 10 for analysis time. Time is money, it's always money. We use hydrogen. So what do we want in terms of efficiency? Small columns, small diameter columns, use the right carrier gas, mobile phase. So there is a coating inside that column. And so that's what we get our separation, right? Our analytes want to go into that coating, come back out, get it out, and so on. Well, how thick should that coating be? I think you can see that the thicker it is, the more likely we are to get some spreading of our analytes. Maybe that our analyte just hits the surface of the coating, comes back out and moves out. Another molecule we're interested in goes in further, then comes out. This one's going on its merry way. We're getting the spreading throughout the column. And so we look at phase thickness too as being an important parameter. The thick phase, we can put more sample on. That more sample may be an advantage, maybe see small things, low concentration things a little better. But again, it costs us in terms of performance. So the thicker that coating inside, the poorer the separation ability. So again, it ends up being a compromise. Too thin, wonderful in terms of efficiency, but we can put so little so little sample on, we don't see it. So there's again an optimum in terms of the phase thickness coating. And for that, we typically do the 0.25 microns. So we do 0.25 millimeter diameter. We do 0.25 micron, actually film thickness. So really, really thin film. So that's kind of takes care of why we pick columns the way we do. How long should it be? Well, back in the old days when chromatography first came about, they were dealing with 6-foot columns. They were made of solid glass. Well, not solid. There was a hole in the middle. So, okay, glass tubing. They were about 6 feet long. Today, most of our columns are 25 meters, 50 meters. We even have a 100-meter column if it's rolled up and put inside that instrument for separation. So longer columns mean better separation. But again, longer columns, if my column's twice as long, my analysis takes twice as long. And again, I'm an impatient person. Let's get this moving. And so we tend to use as short a column as we can get our separation. We optimize the diameter of the column. We optimize the coating choice. We optimize the coating thickness. And then we say, how short can we make it and still do our separation? And you can actually buy a 30-meter column and cut it into 3/10s if you want. If the 10-meter does the job, you basically can buy one column and get 3 out of it. So there's really reasons for that. It's a poor means of getting separation because, again, it costs me time in analysis. So we kind of have the usual. Nothing's free. No matter what you do, you pay one way or another. And so what is our optimum here in terms of capacity? How much material can I put on that? The more material I could put on me, the better chance I have seen peak, but it costs. So here's resolution. Do we really want to resolve peaks? Lots of compounds, lots of small peaks. And so we're going to be working in one direction in terms of all of these parameters. The capacity will work in another direction for all these parameters. The speed is important to us, so separation is easy. We have a different set of parameters. We're looking for trace amounts. So we adjust all those parameters, like the column diameter, column coating, and so on, based on what do we need. If we don't need separation, now we get away from that. We go over to this side of parameters and go for speed. So it's rather interesting. In most cases, we don't necessarily know what we're doing. Maybe I should complete that a little better. That didn't sound quite right. We do know what we're doing, but we do a lot of different things. So somebody will come in. I've had people walk into my office and say, with a piece of drywall from their home and say, Professor Anexis, this stinks. Can you tell us why it stinks? Probably. Okay. So I'm going to be looking for stink in drywall. Somebody else will come in with a totally different problem, different materials, different compounds, different sources. So we tend to choose our columns so they're high efficiency, not super high. We don't choose them so they're super fast. We don't do routine things. If you're working for an analytical company and you do one method all the time, every day, You run 1,000 of these, analyses. You're going to pick your column, and it's going to be optimal for that purpose. We tend to compromise in all of them because we do many different things in our lab. Some basic concepts. I get a kick out of the first one. When we have problems with gas chromatography, 80% of the time it's a plumbing issue, and you need a good plumber to come by and give you a hand. The local plumber may not quite understand your principle, so maybe you need to find a gas chromatographic plumber who knows that can help you. 80% of the time, the problem, if it's not working right, you've got gases in there, they're under pressure, they're making things happen. The gas isn't going where you thought it was. There's a leak someplace. Something's gone wrong. 80% of the time, if you don't get good data, is exactly because of a plumbing issue in the system. You get very good at looking for leaks. Approximately 10% of the time is due to the operator. 80% something went wrong with the machine. The operator should have actually caught that. So we'll give the operator credit for this error too. 10% of the time, operator error. 10% of the trouble is due to hardware. Very seldom it's hardware. We have some old instruments in our lab, and they are as good as they are built today. Hardware is really durable, and so seldom is this ever a problem. You start looking for leaks, you start looking for other problems in the system. You don't look for the instrument as a routine. That time when you don't get the results you want, that 80% bracket, that's where you make the mixture of standards. You make that mixture of standards, known compounds, known concentrations. You inject it into your gas spectrograph. Do you get the separation you want? Maybe you've got a compound that elutes at 2.316 minutes. Is it 2.316 minutes now? It was last week. And so you start looking for those standards, those compounds you injected. Is your peak this big today? And it was that big before? So again, you simply put in standards, known compounds, and see is the instrument doing what it should. If it's not doing, then obviously you start taking a look at what was done wrong. These systems, we've got 3 different gas tanks connected to them. The carrier gas or mobile phase, the air, the hydrogen, and so on. And I think I mentioned that before. These are all sensitive instruments. There are knobs and turn on front to change the flow rates, to direct the flow, and they're all handled with a great deal of care. They're never tightened down tightly. It's always gentle. They are sensitive instruments. One of the first things people do is, crank that one down. Oh, I'll close that one. No, you do it gently. So the idea of operator oversight method quality control samples. So getting the instrument control samples, method quality control samples. If it's a hardware failure, I smile and chuckle at this one because if the machine screws up, I call a friend of mine. I trade him a bottle of whiskey a year, and he comes in and fixes our gas chromatograph. Whatever goes wrong with it, it's hard to beat that one. Except I can't charge the university for it. It always comes out of my pocket. They won't let me buy whiskey for repairs. I don't know why. It makes a lot of sense. No, you get somebody in that knows what they're doing and knows how to fix these instruments. So this just kind of shows some of the places where things do go wrong. So here we got our system again. We've got 54 mils per minute coming in here. And is 3 mils per minute going to go across here and out into the vent? Is the rest of the 51 going to go here? Are we going to get 1 minute here and the rest going out? So that's basically what we're dealing with. Are we getting the flows that we think they are supposed to be? Where can a problem happen? That septum. There's a rubber septum. I'm poking a hole in it every time I make an injection. I may make 100 injections. I may poke 100 holes in that thing. When do we change it? How often do we change that septum? So again, looking for a leak in the septum is one of our first places. We've got a glass tube in here where we really want to see our heating and vaporization occur in our sample. but it's connected to metal. We don't connect glass to metal very readily. And so there's typically a rubber O-ring up here. And if that rubber O-ring hasn't been changed for a while, and believe me, we have seen sometimes where it almost turned into dust before somebody realized they can actually fix it. And so there's again an opportunity for a leak up here. So we can accept them. A leak around the injection port. We've got a graphite seal down here. We've got this very fine column connected here at the bottom of the stainless steel chamber. There's a graphite seal here. And so what you're going to find is that in different places, there's a splitless valve down there that can get plugged up. So you simply go through the highest probability. What's your first choice? That septum seal up there, and you work down for the odds. So again, each of these places can be a problem to look at in terms of making that happen. That happen, meaning have it work properly. Okay. Then I'll spend some time with applications the rest of the time we have today. So I got roughly 20 minutes to look at that. We basically have to do some kind of isolation, some kind of sample prep. We want to look at the flavor of a nice Haralson apple or to pick a different variety. You can't stuff the apple in the machine. It wouldn't work very well. So we've got to do some sample preparation. And so that really does depend upon what the product is. What am I looking at? Am I looking at apples? Am I looking at honey? Am I looking at roasted meat? Am I looking at whey protein isolate and so on? So we're going to have to do some kind of isolation of the sample. And that can be a real problem. And I'm going to spend a little more time with that than I usually do, because it is a problem. And so if you're doing headspace, what do? You put your sample in a closed container, close it all up, let it sit to come to equilibrium. We're doing volatile compounds, flavor compounds. Then you simply take a gas-tight syringe, draw it up, put it into the GC. Very simple, but even that becomes problematic, as I'll mention in a little bit. So we're going to do some kind of sample preparation. And that's really important, that you pick the right methodology again for separation and sample prep, really. This is called actually static headspace, is what I said. You put something into a container, allow it to come to equilibrium, maybe 60 centigrade, something like that. All volatile substances come up and you sample. It's a gas injection, so you can maybe check 1-2 mils of air sample headspace. But there are alternatives. There are two techniques called SPEMI, the solid phase microextraction, or there's a stir bar. And I think I should have looked ahead, how's that? But I think we see all of these methodologies, so we won't go into what they are right now. But you can use this to concentrate your headspace. By SPEMI, you can take whatever compounds are in that headspace and concentrate on those. This is not very concentrated, but this concentrates that headspace. This concentrates the headspace. Another way that we use again Fairmont down in the laboratory is a dynamic headspace. So we've got our container, got our sample there. We can actually put a stream of nitrogen through that sample, have it bubble through it, have it go through the powder, and then any volatile compounds will get into that gas. As that gas comes out the top, as a closed bottle, you can pass that gas through an absorbent material, such as a material called 10X. So you basically concentrate any volatiles that are in your headspace on a 10X. But these also can be used. So we've got some combination that we can use for concentrating a sample to make a better chance of finding things. If you're doing a liquid, so these are all the ways of looking at the gas above a food sample. If your food is liquid, you might be able to use a syringe, but wouldn't be very happy with apple juice and some of these things, so it could be a problem. But if you're looking at some liquid material, you may be able to just take a syringe and make an injection. Solid materials, you can heat the solid material with an inert gas flowing across the solid material, food material, as it's being heated, and collect everything that comes off that sample, everything that desorbs that sample, collected on one of these different methodologies. So there's many different ways you can go around getting a sample to put into the GC. Solid phase microextraction, which is what was on the previous slide, is one of the most common methodologies that are used today. And so this is kind of a funny looking syringe. What it does basically is this top of this apparatus, it's about that high. And so you can push this plunger down, and that pushes out a little glass filament. This little glass filament is an absorbent because it's an absorbent on it. And so any volatiles in your sample will come and get absorbed onto this fiber. Then you pull it out to protect it and put it into a gas chromatograph, a very hot place. And everything you trapped here, collected here, now goes into the gas chromatograph. And so this is a really neat way to get a sample. It's very simple. It's probably my least favorite. It's the most used methodology, but my least favorite methodology. I don't like it because this is a very, very small sample, very thin film. And so it's not going to collect much material. And also, it'll collect the most abundant and most strongly attractive. So it's not going to take a little bit of everything. It's going to take a lot of some compounds, less of others, and less of others. So this fiber down here, it absorbs, but it doesn't absorb uniformly. And so you get a profile. Here's the volatiles in my sample, but they're not necessarily the best representative sample you can get. But it is, like I say, it's extremely popular. In the flavor field, probably 80% of the published work is done using this methodology. 20% uses other methodologies. And someone could say, why did they do that? Why did they use a methodology that isn't ideal? Well, part of it is this is so darn convenient. You're not distilling anything. There's no high vacuum. There's no messing around with all kinds of things. You stick it into a bottle and pull it out. Can't be much easier. No solvents, you name it. And so it's used because it's convenient. There are places where it's right. There are places where you get good data. But all too often, you're really not using it where it should, and you're not getting the data you should. So convenience doesn't necessarily mean it's a good idea. That's one. Here's our stir bar idea. So in this case, we have a glass stir bar. We've all used a stir bar one way or another. This is a nice clear glass, but on the outside, it has an absorbent. And this absorbent, polyvinylsilane. So it's a silane material, so it's a material that has an active functional group. And so we could put it into apple juice. You could stir it for a while in that apple juice. Your compounds that really like that film are going to move into that film. You're going to be concentrated on here. You take it out, you rinse it in water, you stuff it into the hot injection port at 200 degrees centigrade with gas coming across it. Guess what? All the things it absorbed are going to be released. And so it's just a nice way, a really simple way to get compounds out of a system. It's more sensitive than SPME is. It's more sensitive than Headspace is. It's a nice attractive from that standpoint. A couple problems are they don't have many coatings. It's really non-polar. Supposing my compounds of interest are polar, I'm not going to see them very well. And so this will work for some types of samples, but it won't work for all of them. And so you need to know what you're looking for. Doesn't work if there's fat in the sample. If it's fat in the sample, where does the fat go? It goes onto your coating. And then you try to volatilize that inside your gas chromatograph. Not a good deal. So really no good if there's fat. If it's a liquid, no fat, good. You could put that into Headspace, that's good. And so it has its place. I mean, that's the point I want to make. But every method has its weaknesses. Every method has its strength. You need to know what you need to know. In other words, do the right technique, use the right approach. This one actually comes from And I added the things here. We have a large group that's working on plant proteins in one way or another. And one of the things that people are always concerned about, the plant protein, there may be some lipid that comes with that in the isolation process. If there's some lipid, you go through this whole isolation process, you produce a dry protein isolate. There may be some lipid in there. Now that lipid is going to oxidize with time. And so how do you test for oxidation? How do you test to see if that protein isolate is very stable to oxidation? And a simple way to do that is, again, using gas chromatography for that purpose. And so the methodology that's typically used is to place your sample. So you got your protein isolate, put it in a glass vessel, seal it with a nice septum closed system, add an internal standard. You want some reference compound at a known concentration. That's really important, is to have a standard in there to base quantities. If your peak is this big, okay, is your standard that big? Is it what happened about our sampling? What happened in our gas schematic? So you always put an internal standard in there to get an idea. Then equilibrate at some time and temperature, that may be 60 degrees centigrade, for example, maybe 45 to 60 minutes at that temperature. That gives you time for any oxidation products in that isolate to come into the headspace and come to equilibrium. And then you simply draw off some of that headspace and analyze it by your gas chromatograph. So very, very simple methodology. You then typically look for hexanal. Hexanal is a good indicator of oxidation, good triglyceride oxidation. So that's most commonly the compound that people look for. When you look at the ratio of this to the known concentration of that, we can calculate the concentration here. You look then, of course, at the chromatogram. You always look at a chromatogram. It spits out numbers. It does some math for you. But you always look at the chromatogram. Are the peaks shaped right? Is there two peaks there instead of one? Again, a person always has to question every bit of data that you get. Resolution, peak size, it really seems simple. It seems like a nice way to do this. And it really is. But again, any methodology used, I don't care what it is, you need to know what you're doing. You need to know what the pitfalls are in that methodology. Because you can be doing things that seem really right and find you miss the point. In this methodology, putting things into a bottle, closing them up, come to equilibrium, well, septum leakage, that can be a problem. If you've sampled that vial more than once, sampled a couple times, well, there may be a leak. Well, okay. Let's say we've got a leak point. This one's interesting to me. You've got a flour or an isolate, if you want to call it. And so does your limonene oxide and does your hexanal, it's limonene oxide up here. That's what I look for in flavor compounds. Does it migrate out of that dry powder to get into the headspace? So are things inside? You've spray dried. This is a powder. There are particles. And so there's going to be lipid on the inside. If that oxidizes, is it able to diffuse out of that particle? Or isn't it? So are you measuring just the fat that's on the surface of the particle is oxidation? Or are you measuring the oxidation of the mass of lipid also inside the powder? So you have to think about that. Maybe that powder, typically it's analyzed in powder, maybe it should be dissolved in water. If it's dissolved in water, you completely break down the structure of that spray dried powder, and you know that hexanal is going to come out and it's going to be measurable. So again, the idea should be solubilized to make sure hexanal is released. Should it be left as? If your sample has variables including fat, supposing I've got a protein isolate here with 0 fat, 5% fat, and 10% and 20%. So if you have this exactly same material but different fat contents, and you will expect to see very different results from each of these because there's any fat. The fat's going to love hexanal. should love hexanol. So the high-fat material is going to absorb hexanol, and it's not going to let it go. So if you got the same results across all of them, something's wrong. And again, you need to think of that when you're doing these types of methodologies. So again, if you've got exactly the same material, okay, but if I got a different material comparing this isolate to that isolate to a different isolate, they get different fat content, you need to take that into account. One thing I somehow think it's interesting today. In 2009, I published a paper looking at the encapsulation of flavoring materials and lipids in protein solutions. And so my whole goal was to say, is this oxidizing? How fast is it oxidizing in storage? So prepared material, spray dried the powder. So I have a powder based on a protein plus fat, another protein plus, let's say, flavor molecules. So I've got these materials. I sample them at every period. So put them in storage and go ahead and sample them. And that protein gave me beautiful results. I found very little hexanol over its shelf life. And my control was gamma acacia or modified starch. That's traditionally materials used for encapsulation. Protein isn't traditionally used, but protein's cheap. Well, it's not cheap, but it looks good on the label. Plenty available. They don't have to put a chemically modified starch on the label and so on. So protein's attractive. But what I found is that protein really did look good. But 2 years ago, I did another study and I found out that their hexanol was reacting with the protein. So my marker was being chemically reacted with the protein. And that's why it looks so darn good. It wasn't so good. It wasn't a miracle that preserved the sample. Chemically reacted my marker. Nobody ever figured that out before, including me, by the way. And so that's really an interesting one. I have a master's student working on that now, saying, what are those? How do we manage? And so, again, I mentioned surface oil. If your oil is on the surface, and it's going to oxidize more quickly if it's inside. So you need to know where your oil is. You need to know the oil content. You really need to know what you're looking for. And what concerns me is that all too often a person will use a method, and you'll get some data, and you say, wonderful, I'll go away with it. You can't do that. You really can't do that. Anytime you're doing an analysis, you need to know what you're doing. You need to know the pitfalls. You need to take good care along those lines. And that requires that you know gas chromatography really well. So that's why you're all sitting here, right? Maybe it's required. Anyway, it's you just have to be careful and think about what you're doing. Think of all the options. Don't do things blindly and take a number and go with it. So in our area, what do we have? We've got another 5 minutes. Aroma research. This particular organisms will ferment oleic acid to a key lactone. And it's a coconut lactone. If you smell that particular lactone, it smells exactly like coconut. There's a real demand for coconut lactone in the industry, coconut flavor. And you can form it, not from coconut, but you can form it by fermentation of oleic acid by particular microorganisms. But what you have to know is that lactone can be either chiral form. It can be this chiral form or that chiral form. And depending upon the chiral form, it's a good flavorant or it's a bad flavorant. So how do you determine the chiral form? That's not easy. It's typically fairly complicated, but again, you can do it by gas chromatography if you have the right system with the right column. And this is just simply outlining. You take your culture, you extract it with diethyl ether. You take the diethyl ether, you can it, you concentrate that down to 0.2 mils. Fraction it in a silica gel column to get out only the fraction you want that has your lactones of interest. Concentrate and run by gas chromatography. You have to have a special column called a chiral column, and that will actually be able to set chiral isomers not a simple task. Here's the S and the R form over here, the S R form here of these lactones. So again, a tough analysis, but it could be done relatively easily by gas chromatography. This is one looking at a residual treatment of apples to control apple scald. Apples are dipped in 1 gram per kilogram solution of, where to go? Oh, diphenylidene. There we go. It was up on top in big letters. So, okay, make a solution of this. The apples are treated with it, and you don't get apple scald. Okay. But of course, the FDA says there's a residue limit of no more than 10 parts per million of this as a residue on apples as we consume them. This is a really simple methodology in terms of isolation. I love it. Simply wash the surface with a solvent. Okay, diethyl ether is always a nice clean solvent for that purpose. So you kind of wash the surface, take that chloromethane. Okay, this is hexane they happen to use. Concentrate the sample down some, and then inject it into a gas chromatograph and look for your particular compound. But when you do that, and this is the surface of an apple, guess what? There's an awful lot there. It's not just your diphenylidene compound. We have a ton of other compounds that come as well. And so where in all this is my compound of interest that I have to control? And so, of course, you find that by adding standards. That's one way. But another way also is to go ahead and use a mass spectrometer, so use an MS as a detector. And so you can go make your injection into the GC. You tell your GC that we want to keep looking for this, look every 100 times a second. Let's say you take and look for this fragmentation pattern, and you can then find that particular compound. In this case, we actually tell the mass spectrometer we've got complete spectrum, but I want to see how mass 169 changes during the run. Are there any compounds that have mass 169? Because 169 is characteristic of this diphenylidene compound. And so here's a time between 16 minutes, 17 minutes, 18 minutes of gas chromatographic run. We get our peak show. And so again, you can go ahead and run a sample. You can spike a sample with your diphenylidene to get a little bigger peak. But simply by looking at 169, you don't find that other places. And so it's unique. It's an easy way to find which one of those peaks actually over time have your diphenylidene. So a nice, again, place where mass spectrometry comes in and says, let's look for one particular compound. I think you're going to be doing lipids in class. So you're going to look for fatty acid profiles. I do have something on that, but we're not going to be able to do it in a minute. So let's leave it, and we're just going to assume that I don't know who's helping you with Kat or Cindy or someone's helping you with it. But again, you'll be using GC for a look at fatty acid profile of different materials. So you've got the methodology, and you're going to be running the GC for that purpose. So have fun. Have a good day. Are you on duty?
I am on duty.
Good. Because I don't have a faintest idea what to do.
It's okay.
When I found out I wasn't going to be teaching regularly,